Hello everyone, I'm Yinda. So today I will present the paper OctoSketch, enabling real-time continuous network monitoring over multiple cores. This paper is in collaboration with Peiqing and Professor Zaoxing from the University of Maryland. First, let's begin with the motivation. Due to the trend of visualization, many network management applications have started monitoring network traffic within software platforms like OpenVSwitch. Moreover, with the slowdown of Moore's law and the rapid adoption of high-bandwidth links, a single CPU core is no longer sufficient to saturate network bandwidth. Network applications nowadays often use multiple CPU cores to process hundreds of Gbps traffic and achieve line rate. Furthermore, various network management or security applications operating within software platforms require visibility into various aspects of network traffic. For example, certain load balancers must identify heavy hitters and redistribute these large flows to achieve load balance. Similarly, a anomaly detection system may need to identify super spreaders, which could indicate malicious activity. Consequently, there's a pressing need for efficient traffic monitoring to aggregate statistics across multiple cores. Maintaining per-flow statistics with full accuracy on every CPU core consumes excessive resources. Therefore, sketching algorithms offer a promising approximate solution for estimating such statistics as shown in prior works. Consider the counting sketch, which can be used to count the number of packets in each flow as an example to demonstrate how it works. This sketch consists of arrays of counters. For each incoming packet, the flow ID is extracted. Using independent hash functions, the flow ID is mapped to a counter in each array, and the counter is updated. If we need to identify large flow with many packets, we often need additional data structure, such as a heap, to store these heavy flows. We use a minimum hash counter as the estimated size. If the estimated size is large enough, like larger than the minimum size flow already stored, we put the key into the flow key storage. The key advantage of the sketching algorithm is its ability to achieve high throughput with a small memory footprint and a bounded error rate. However, scaling from single-core telemetry to multi-core telemetry is not as straightforward. A stronger solution to apply sketches in the multi-core scenario is to divide different keys into different cores. For each core, we can maintain a sketch for tracking the key distributed to it. Because the keys in different sketches never overlap, the applications can get the statistics of a specific key by querying the corresponding sketch. However, stringing pinning the key to a core can lead to degraded packet performance. As shown in prior works about dynamic load balancing, when the skewness of the network traffic varies, key-based partition often lead to high load imbalance among cores. Moreover, depending on the definition of key, it is sometimes infeasible to pin a key to a core. For instance, a NIC may distribute packets based on 5 tuples, while applications may want to measure the key based on the source IP. As shown in prior works, multiple applications require measuring results based on multiple different key definitions, and we cannot guarantee the key distribution across these different keys. As a result, in this work, we do not make any assumption about the way of distributing keys to accommodate various network applications. Many existing systems utilize the entire sketch merge design to scale their operations to distributed settings, which can also be applied across multiple CPU cores. In this design, there are multiple worker CPU and an aggregated CPU responsible for aggregating statistics from the workers. Each worker maintains its own sketch to handle this traffic and periodically sends this sketch to the aggregator. The aggregator then merges the sketches into its own sketch and reports the aggregated results. These sketches can often be merged using operations such as sum and max to obtain the aggregated results without compromising accuracy guarantees. For instance, in the case of the counting sketch, the aggregator can aggregate results by calculating the sum of the two counter arrays. The entire sketch merge approach, while effective in aggregating statistics, can introduce significant overheads on the aggregator and increase estimation error. Our goal is to make the accuracy of the entire sketch merge approach as close as possible to the ideal scenario where the traffic is not distributed. However, frequent merging of entire sketches like merging every microsecond, is computationally expensive for a single CPU core. On the other hand, infrequent merges conserve resources, but can lead to stale query results at the aggregation. We found that the current CPU cannot support such a high frequency of merging to achieve comparable accuracy to the ideal case under the line rate of 100 gigabits per second. The inefficiency of the entire sketch merge approach stems from the fact that not all counters are equally important for query accuracy. Due to the skewed nature of the network workloads, counter values in sketches often exhibit a heavy tail distribution. For instance, when using the count me sketch to identify heavy hitters, more than 80% of counter values may remain unchanged at the aggregator, while some counters experience changes greater than 1,000. In other words, the aggregator spends significant computational and communication resources merging counters that are not important, thereby delaying updates from crucial counters, which lead to stale query results. Another challenge with the sketch merge approach is that each worker must maintain an entire sketch instance, which include both the counter structure and the flow key storage. Previous studies have identified flow key storage as a performance bottleneck in sketches. Managing this flow key storage per core is computationally intensive, especially considering the high volume of traffic in network environments. In summary, reusing the sketch merge approach cannot achieve good performance. In this work, we designed the OctoSketch, a sketch framework for multi-core monitoring that can achieve guaranteed accuracy at any given query time, be adaptive to packet arrival rate, and maintain high performance. First, OctoSketch adopts a continuous change-based mechanism, where each worker only sends sufficiently changed counters to the aggregator to achieve high online accuracy. As the entire sketch merge expends significant computational and communication resources, merging counters that are not important, OctoSketch essentially amortizes the large sketch merging operation into a series of individual counter change notifications. Specifically, OctoSketch keeps track of individual counter change in the sketch for every packet, and send the counter when the change is sufficiently large. In other words, we only send counter with the most critical informational value for online accuracy. Note that the definition of sufficiently changed could vary across different kinds of sketches. To achieve generality, we discuss different kinds of sketches in our paper and make sure that the OctoSketch can be applied to a broad spectrum of sketches with some additional modification. In our paper, we apply OctoSketch to 9 representative sketches across 6 different tasks to demonstrate the generality. Please check our paper for more details about these different kinds of sketches. We also provide an analytical proof demonstrating that, by using this continuous change-based mechanism, OctoSketch can maintain the same asymptotic error bounds as in the ideal scenario where the traffic is not distributed. It means that when queried the OctoSketch, the aggregator can deliver results that represent the aggregation of traffic from all cores within a bounded error at any given query time. Furthermore, OctoSketch can offer such accuracy guarantee across a range of measurement tasks, including identifying heavy hitters and estimating cardinality. Second, OctoSketch dynamically allocates resources between workers and the aggregator to fit the packet arrival rate. For example, when the packet rate is low, the OctoSketch can ask workers to send changes more frequently to achieve high online accuracy. In particular, we set a universal threshold for all workers to adjust resources. All workers will reach that threshold. If the changes are larger than the threshold, the workers will push counters to the shared queues. To achieve the best possible online accuracy, the aggregator pulls counter updates from workers as much as possible. The aggregator also periodically measures the queue length and modify the threshold. When the queue length is small, the aggregator will decrease the threshold to receive more frequent counter updates and achieve a higher online accuracy. Except for the best possible online accuracy, OctoSketch can also support different policies of resource allocation to meet different kinds of system objectives. For example, when there's not much traffic, OctoSketch can also choose to free up some extra computation resources based on the accuracy target. Specifically, we can calculate the lower bound of the sending rate based on the accuracy target. The sending rate will not further decrease if it is smaller than that bound. Finally, OctoSketch reconstructs workers and the aggregator to remove redundant data structures and achieve high performance. As maintaining flow key storage in each worker and aggregator is compute heavy, OctoSketch reconstructs sketches and remove flow key storage in the workers. Specifically, since the traffic statistics are calculated based on the aggregated flows, only the aggregator needs to maintain the flow key storage. Each worker eliminates the performance bottleneck of maintaining complex data structure and only sends potential heavy flow keys to the aggregator. Due to the efficient continuous change-based mechanism, the counter and key updates will not create additional burdens on the aggregator. Then let's discuss the evaluation results. Our evaluation covers implementation on 3 diverse platforms and the application on 2 use cases, load balancing and key value caching. We compare OctoSketch with both the entire sketch merge and the ideal case where the traffic is not distributed. We use 1 aggregated CPU and vary the number of worker CPUs. The merging frequency of the entire sketch merge is set to the maximum supported by a single CPU. First, we compare the online accuracy over the total number of packets received by workers. We use the OctoSketch for the count-bin sketch as an example. We can find that in terms of the absolute error of the estimation of heavy hitters, the error of OctoSketch is close to that of the ideal one due to its continuous change-based mechanism. In contrast, sketch merge accuracy fluctuates significantly over time. Its error drops once the aggregator merges sketch and keeps increasing until they merge another one. The large merging delay makes the accuracy far from that of the ideal one. We also show the OctoSketch can achieve good performance on different platforms. We use the DPDK as an example. OctoSketch achieves higher throughput than the sketch merge. Specifically, the throughput of the OctoSketch is around 20 millipackets per second higher than that of sketch merge when using 6 workers. In addition, the CPU usage per worker of the OctoSketch is around 20% lower than that of the sketch merge when using 6 workers. In summary, removing redundant data structure on workers enables OctoSketch to achieve higher throughput and lower CPU usage in DPDK. Finally, we demonstrate OctoSketch generality by applying to 9 sketches across 6 measurement tasks. The OctoSketch can bring significant accuracy and throughput improvement compared with previous sketch merge. For certain sketches where there is no flow key storage, the OctoSketch may not bring throughput improvement, while its overhead is lower than 10%. In conclusion, our paper addresses the challenge of multi-core monitoring, demonstrating that reusing sketch merge for a distributed system can result in significant overhead. To achieve high online accuracy, optimal performance, and broad applicability, we propose OctoSketch. OctoSketch leverages a continuous change-based mechanism, eliminating redundant data structure, and dynamically allocating resources among workers and the aggregator to meet diverse system objectives. Our results demonstrate that OctoSketch achieves around 15.6 times lower errors and up to 4.5 times higher throughput than prior entire sketch merge. The source code for OctoSketch is now available on GitHub. That's all for my talk. Thanks for your attention.